much. As Adam pointed out, I'm doing a PhD here with Adam and Anil on consciousness measures. So in the Sackler Center, we have all sorts of different subgroups, and I'm with the theoretical guys. And we are trying to look at measures of consciousness. So what are these different levels of consciousness you could have? So for a clinician, there are, of course, these big categories. For instance, at the y-axis, you have the intensity of inner mental life, let's say, or awareness. And on the x-axis, you have vigilance or arousability. So most people would agree that if you are in a coma, the intensity of your inner mental life is, of course, less than in conscious wake. So your subjectivity is extremely reduced. There's you don't hear any sounds or sights of life when you're in a coma or in general anesthesia. Now, there are, of course, other states where you may have a very rich inner mental life, such as here in the locked-in syndrome, but externally you're not arousable. You don't show any signs of being awake. You're not walking around or moving in the way you would normally. But internally there's a lot going on. So that's why behavioral correlates of consciousness play a big role in the clinic. So there's a Glasgow coma scale with which you just check if people react to certain tasks. Yeah? If they just respond, for instance, when you talk to them, that's a pretty good sign that it feels like something to be this person at that moment. Now, besides behavioral correlates of consciousness, there are, of course, lots of machines with which you can go and hunt for neuronal correlates of consciousness. So what are the signatures that are only there when people are aware and conscious, and that are never there when they're unconscious, as defined by this clinical course classification of conscious states? And of course you have all sorts of modalities, from some that are invasive and those that are non-invasive, with varying spatial temporal resolution. So now I'll first give you a few examples of each of those and how each of those is kind of used to find signatures of conscious level. For instance, very straightforward one would be just to look at overall metabolism. And then you see already there's a lot of metabolism in normal consciousness and dreaming, REM, but also when you recover from your propofol, for instance, or any other anesthetic. And there's less overall metabolism in the other states. So it's particularly difficult to distinguish, for instance, the vegetative state, or also known as the unresponsive wakefulness syndrome, from recovery from vegetative state. And those are the clinically, of course, highly relevant cases. Yeah? If you have, let's say, some family member and he's in a coma, and you don't know whether he will ever wake up again. So you need to have some sort of tool, some sort of judgment that tells you, does it make sense to keep this patient running, or let's say, provide the patient with all sorts of life support or not. And this is, of course, the trickiest bit for the measures of conscious level. So to distinguishing these two very close conscious states, one where there's no inner mental life whatsoever, and the other one is just a little bit minimally conscious state, just recovering from it. Now, one could also just apply brute force and look at the EEG recordings and do machine learning, and without knowing which features you actually pick up in the EEG signal, just try to find some reliable classification for these states. And there are these machines in pretty much all hospitals called bispectral index. It's one of the most widespread ones, but those machines have considerable drawbacks. That they don't always work so well. So, for instance, 9% is always wrong, and there are special cases, for instance, for kids and special anesthetics, such as this halothane, where it doesn't work at all. And it's also not very interesting for people who are interested in the theory of mind, theory of consciousness, because you can only advance these theories of consciousness if you have a well-defined signature. Only then you can say, does this signature, is it in line with my theory of consciousness or not? And for this brute force blind feature extraction method, you do not know what is actually the feature that correlates with consciousness. So more interestingly would be methods where you can actually extract particular features. So here in this video you see the activity in a mouse brain. You know, on the top panel you have here anesthetized mouse brain, and that's optical, so that's actually real time. You know, you see the second a little bit slowed down maybe. And how they did it is you can make neurons become voltage sensitive fluorescent. So you actually thin a little bit of the skull of the mouse, and then this genetically modified mouse is such that its neurons only reflect light back if the voltage is high enough, and that's how you can visualize the neuronal activity. And if you just compare the two, on top you have the anesthetized case, and you see that for the binary one you saw kind of big waves sweeping through, and for the awake one you have less of this kind of big wave phenomenon and more diverse and small waves. And you could then try to define it. How exactly could you measure this? And then these people came up with a definition of avalanche. You just look at these pixels, and it's kind of not working. Here, okay. You look at these pixels and how they spread with time, and then you can define an avalanche, and you compare simply avalanche statistics from these two states, so anesthetized here and awake there. And then you see, for instance, in the anesthetized case, there's just more of the really long avalanches, which was already apparent when you just stared at the video. You kind of saw these big waves sweeping over. This whole analysis, avalanche analysis, is also connected to people that like the word criticality and talk about that. Because it may be an index of scale invariance. So, and here they also do a little bit the scale invariance argument by changing the pixel size of their video. And they show that for the awake case, it's kind of scale invariant. You always have here the same index k, and for the other one, for the anesthetized case, it does depend on the scale, so which is kind of interesting. Other people try to go more directly at the time series and just look how messy is the time series, how random is it, and can we kind of measure this simply by Shannon entropy. So you have some sort of EEG time signal like that one, then you discretize it by putting it into, let's say, a bunch of bins, just by voltage you could bin it, no? And then you get some symbolic sequence. And having such a symbolic sequence, you can simply count how many, let's say, A's are there, and divide it by the complete length of the sequence, and that's your probability for the symbol A popping up. And like this, you can do this for all symbols J, and then you get the Shannon entropy of such a sequence of symbols. And this Shannon entropy does correlate with consciousness as well. Here you see the concentration of the anesthetic in the person, and there you see the Shannon entropy of the EEG recording, and it kind of goes down as the concentration of the anesthetic goes up. And then you have various ways of computing this Shannon entropy. You can also just look at the spectrum, for instance, and look at the spectral entropy. And most of them do pretty much the same thing. They kind of go down when the anesthetic kicks in. There is also some theory behind it where people try to speculate, like Card Harris in London. He comes up with his entropic brain hypothesis and just says, you can linearly try to classify states between very low entropy, low disorder, and rigid states. So it also is inspired from the phenomenologies from inside, whether you you're very flexible in your mental processes, like in whatever the psychedelic state. You're very jumpy in your internal perception, or you're, let's say, quite the opposite, very rigid and not much going on, like let's say in a seizure or deep sleep, or not conscious at all, as in those states here. So it's of course interesting always to have some signature you measure with some device and then trying to connect it to some theory of consciousness. Now, another thing you could simply do as simply as computing the Shannon entropy is to look at compression of the signal. You know, for those who use Linux, if you do a file compression and then you can just choose, you know, what kind of compression algorithm do you want to compress it. Zip is kind of the most common one. The others work more or less similarly, so most of them are based on Lampel-Ziff compression algorithm, whatever, in the 70s. And this does, in essence, the following. So here's a simple implementation of it. So you have some string, let's say a binary string as here, and according to, you know, with this algorithm, you come up with some dictionary, and then you go through the string, and for each element in the string, you check whether it is already in the dictionary or not. And when it's not in there, then you add it to it. So that's kind of hand-wavily what's going on. So given a string, you get a dictionary, and it kind of creates binary words. Yeah? And the dictionary is a certain length. So for instance, 8 for this particular example, which is ordered. Yeah? 10 zeros at the start and 10 at the end. Now, if you shuffle it in time, then your dictionary will increase in size. It's 11 instead of 8. So this kind of method does not only capture kind of diversity in amplitude, but also diversity in time. So you kind of have in Lampel-Ziff compression a very good approximation of Kolmogorov complexity. So how complicated or how random is a sequence of strings. Now, very different to entropy, because entropy of these two strings here would be identical. Yeah, entropy doesn't matter where the symbols are. Entropy just measures how diverse is the alphabet, so to speak. Now, this measure has already also been applied to time series to measure conscious levels. So in 2001, for instance, by these people here, different anesthetics, you know, also propofol and sevoflurane as well as these other two, and it kind of works quite well. So here you get always sensitivity and specificity of the measure, and they're all quite high. Also a little bit later, so here you have once again Ramsey's scale. So Ramsey scale 6 means that it's completely unconscious, doesn't respond whatsoever to any external stimulus. The complexity goes down significantly, and it's very high when the people are conscious and in wakeful rest. So Ramsey scale 1, so to speak, is here. Ramsey scale 2, 3, and then he passed out completely and doesn't respond anymore. And the Lampel-Ziff complexity is very low then. So ever so often, you know, as there are so many measures, you know, people try to give an overview and just show how many different things you can do to distinguish different states. So these plots here are area under the receiver operator characteristic curve. Maybe you notice AROC plots to see how good is a measure to distinguish two states. For instance, how good is this measure to distinguish vegetative state from conscious state would be a blue dot, and if it's close to 1 or 100%, then it's very good in distinguishing, but it could also be, if it's close to 0, it's also good for distinguishing, but inversely so. So if a dot is close to 50%, it's a very bad measure. It doesn't discriminate whatsoever, it's just random. And you see there are lots of spectral measures. You could just look at the power spectrum of diverse time series, and this kind of works more or less. So of course the blue one is kind of the easy one. Vegetative state and conscious state is kind of as extreme as it gets. But tricky is the red dots, because that's vegetative state and minimally conscious state. It's just, you know, the transition is. But this is the clinically interesting bit, because here you need to decide, do we keep the life support on for this patient or not? So this is exactly what the clinicians are really aiming for. Interesting about that is not only that you have kind of, you know, you have sorts of spectral measures, also looking at event-related potentials such as particular waves, also information theoretic measures. So this K complexity is actually the Lampel-Ziff thing I just showed you guys. Kind of does all right here. Interesting also, you can just look at the fluctuation across trials and just use the fluctuations as a measure, and then kind of works nearly as good as the measures themselves, which is surprising. Another, you know, you see below is then across sensors, that you not only look how does the measure score in time, but also or for a single time series, but here how does it work if you look at several time series at once. Now, one more example is, for instance, for an information theoretic inspired measure of conscious level is symbolic entropy. So weighted symbolic mutual information. Weighted symbolic mutual information is such that you have a time series and you kind of try to binarize it into motifs. So you need some sort of tau here, which is your time step, and then you look whether these three next measure points in your time series are, let's say, in this shape, or in that, or in that, or in that. And like this, you can get such a sequence of symbols here. And now we can compute the probability of certain pairs popping up at the same time, and that's their proxy for weighted symbolic mutual information. I just showed their result. You know, you also can use it to distinguish these, also the difficult ones: vegetative state, minimally conscious state, and consciousness. And the main outcome is that stronger long-range weights are in their plots of weighted symbolic mutual information. And they try then to connect this finding with global workspace theory, which is a theory of consciousness especially brought or developed by De Haene and others, or especially supported by De Haene experimentally with all sorts of priming experiments. And in essence, they say you're conscious whenever you're conscious of a particular percept. So every 50 milliseconds, you look around and you're conscious of something else. And this particular concept you're conscious of is then broadcast, so across the whole brain in some sense. And they try to see, okay, when there's lots of these long-range connections, then there's more of this global broadcasting going on, and that's why the conscious level overall is higher. So it's a bit their logic. It's just another example how people try to A, come up with a measure that really works with conscious level, and B, try to connect it to some theory. Now we come to the best consciousness measure so far out there. It's Casali and Massimini. So it was a science paper 2013. What they did is they had a combination of TMS and EEG. So you have an EEG cap and you get a magnetic perturbation. So this, for instance, a time series here. And then here you get a small magnetic perturbation. And then the brain, there's some reverberating response signal from the brain. You know, you just kind of, you perturb the brain, then you look at the response. And if the response is very, goes to all regions, then they say it's a very integrated response. And if it is hard to predict and very diverse, then they say it's a differentiated response. And they do so by binarizing with a threshold that binarize for each channel the response, and then they get some binary, multidimensional binary time series. And then they compress it once again with Lempel-Ziff compression to see how integrated and differentiated the response is. Now this method works surprisingly well. You know, here are the subjects, 32 subjects, and you have NREM sleep. Here's always unconscious, and there's always conscious. And the different symbols are just the different spots where they give the magnetic perturbation, you know, here, wherever the targets. Doesn't really matter. And what matters is that you get a very clear separation between wakefulness and unconscious, you know, NREM, sleep, and anesthesia. It also works for dreaming. Yeah, dreaming is up where awake was before, and also for the very tricky disorders of consciousness, where you kind of are in between, yeah, from unresponsive wakefulness syndrome over minimally conscious state to emerging minimally conscious state, and then locked-in syndrome, where the people are actually as conscious as normal people, but cannot move any muscle anymore. So that's the best consciousness meter out there. And they try to connect their findings to integrated information theory by saying if the causal interactions between brain regions are both integrated and differentiated, then you're conscious. That's kind of the gist what Tononi and now also Christoph Koch try to come up with their IIT theory of consciousness. So in essence, they say if the causal architecture of any system is of a particular complexity, then it feels like something to be the system. So that's kind of their fundamental proposition of how consciousness works. So that's quite interesting. We were inspired by this result and thought about, okay, how about looking at such binary multidimensional time series and looking at Lamp-Ziff compression of this as well, but just spontaneously, just looking at the spontaneous activity, so without any perturbation. And in order to capture diversity over locations as well as time. And we did so by coming up with 3 new measures. So the first one is synchrony coalition entropy, second amplitude coalition entropy, and the third is Lamp-Ziff complexity concatenated over columns. That's a little C here, and I'll just walk you quickly through what's going on there. Synchrony coalition entropy is such that we take 2 time series, and then we look at their analytic signals. So remember, analytic signal is something like that. You have here, for instance, just as a quick example, the green one is the absolute value of the analytic signal of the blue one. So it's related to the Fourier transform. So f is Fourier transform, and the u here is a step function. So you kind of get rid of all the negative components. And what you get from the analytic signal of a signal x is just the same signal x as its real part, and then you get the Hilbert transform of your signal x as the imaginary part. Hilbert transform was this thing here. You just get a convolution with a function of 1 over t. So for a pure sine wave, it's pretty boring because then you just get a constant as the absolute of the analytic signal. But for some real time series, you see that it's kind of flipped upside down. Everything is negative, it kind of goes up there, and that may then you get a better way of representing the activity of this channel. Now, once you have these analytic...
So what's the goal of that transform? It's just to get the absolute value of the signal.
Yeah.
That's the way of getting the absolute value.
Yes,
of the signal.
to measure the amplitude, rather than just you could also just see whether it's positive or negative. But this is a more
smoother.
Yes.
You don't get these kind of flips at the
Yeah.
axis. So.
Yeah. Okay, and as those are complex, you have phases. Now what this particular measure does, SCE, or what's going on here is, you look at, here's the time series. For a particular time point, time t, for instance, you look at those phases. Now there are complex numbers, hence you can check the phases. If the phases are, instantaneous, phases are close enough together, then you say there shall be a 1. And like that, you get for every pair of time series, you get a binary synchrony time series. Now, having such synchrony time series, you get for a particular channel, let's say the ice channel, you get such synchrony time series with all other channels. And then you can see how diverse is this. And in order to check how diverse this is, you can compute the entropy. Once again, you could just map, for instance, such a column of binary, such a binary column you can map to some integer, for instance, by this bijection. Doesn't matter what bijection it is. The only point is get some bijection to get one symbol for a particular column. And then you get once again your sequence of different symbols, and you can compute the entropy of this symbol again. This is what we call synchrony coalition entropy. Now we have another one, Lamp-Ziff complexity, but this time of the whole sequence. And here what we do is we start off with some time series, and we look at the absolute value of its Hilbert transform. It's this here once again, and then we look at the mean here. And if the signal is below the mean, we get 0, and if it's above the mean, we get 1. So we just can binarize such a time sequence in this way. And this we can do for all channels, and then we can concatenate it column by column. Okay, here we binarized each channel, and then we concatenate it to get one big long binary sequence. And then once we have this, we can compute the Lamp-Ziff algorithm I showed earlier, which tries to find binary words and then look at the size of the dictionary again, and this gives us kind of the complexity or randomness of that sequence. Sorry.
I'm just curious about why you use the mean rather than the median. The median will give you a maximum
Would work as well, probably.
distribution by definition, preserve more
Yeah, I mean, the people who applied it earlier experimented around with different threshold procedures, and it doesn't matter that much. But sure, there are other ways to improve your accuracy and be, for instance, more noise resistant. So that may help here. Also another point just in this direction, they also used, of course, to put it into more different symbols, using the concept you saw earlier with the symbolic binarization. And this was shown in the paper that it reduces the sensitivity to noise. Okay, so what?
Important point there, which is that we normalize with respect to the source entropy. So whether we take the mean or the median, it's normalized with respect to the overall entropy rate. So if we were to choose a different thresholding that varied the proportion of zeros and ones we end up with, we normalize by the maximum possible complexity you could possibly have for that given proportion of zeros and ones.
Cheers. So, and we applied these measures as well to data, for instance, to EEG data on propofol anesthetized healthy subjects. And you see already, if you just look at the time series, that here you get, of course, it looks already here a bit more random and more diverse. If you just compare the spectrum, here you get more low waves in the anesthetized case as opposed to the wakeful rest case. And it works quite well. So for all subjects, the blue dots are the scores for our 3 complexity measures for wakeful rest, and these dark red diamonds represent their scores for general anesthesia. Now, a second data set we applied these measures to was depth electrode recordings of epilepsy patients. So these unfortunate people have deep pins in their brains for pre-surgical evaluation, such that the surgeons know where to cut. And they stay in there for a few days. So you get depth electrode recordings of different sleep phases. And sleep is, of course, a good example for falling into unconsciousness. That's what's happening to all of us every night. And also here you can just look at the time series, just an example of these recordings, and you see that once again, if you are in early night, non-rapid eye movement sleep, you get more slow waves as opposed to in wakeful rest or in REM. Now the outcome, the results are very similar to what we found for EEG. So once again, for these 10 subjects now, this is normalized by the score for wakeful rest. We see that wakeful rest and REM have kind of comparable complexity for most measures in all subjects, and there's a very clear distinction once again between wakeful rest and non-REM early. These dark red dots are always for all subjects far away from the blue ones. Now, we also get some whole night recording. You get some sort of hypnogram. These people sleep in different sleep phases. Sometimes they wake up. And this particular patient had also parasomnia events. The parasomnia event is one when they are fully aroused but not conscious at all. So, and for those, the consciousness measures are kind of lowest. Which also makes sense, if you look at that here, it's pretty low, parasomnia, what these people find, so it kind of matches pretty well this overview. We also looked at just the power spectrum. What's the effect actually of the different frequency components on our measures? So if we throw away all frequency components that are below one of those thresholds here for high-pass filtering, then we see that the effect in group level kind of becomes weaker. So the lower frequencies are especially for this depth electrode data set, important for the effect we measure. But it's still there also if you throw away everything below 10 hertz, for instance. The blue is always higher than the red thing. Now there are other features you could look at in sleep. Time series, slow wave sleep spindles. Here's once again such a hypnogram, what sleep state are you over the night. This kind of time is x-axis, so whatever, one night, 8 hours or so. And here you have the different states, you're awake, then here you're dreaming, then here you go into these deep sleep phases, then you dream a little bit, deep sleep, and so on. And then you can see which other signatures kind of indicate these things. For instance, you find alpha rhythm very strong if you're awake, and you find sleep spindles popping up when you're in light sleep and other stuff like that. What's interesting about those is that the sleep researchers suppose they were very local effects. Huh? So for instance, sleep spindles do not show up everywhere in the brain, it's just in certain regions. And they also use depth electrodes, especially those with little tiny wires, such that they could actually probe single spike activity as well. And so Nia and Tononi, they have the they're sleep specialists, and they found that sleep spindles are a local effect. So we asked also, is our complexity measures is also a local effect, or is it just a very global thing? And why are we asking so? You know, because the whole connectome business, sports especially, they always try to connect, of course, infrastructure and traffic. If, for instance, your connectome has a particular shape, then maybe also the activity that you measure with functional connectivity measures will have a similar shape. So there was one motivation to look more locally. Now, what we did is we looked now for all these patients, where do actually these depth electrodes sit? Yeah, you can classify them in a few regions, and then look where do they actually sit. So it's quite diverse amidst people. And we try to try now different regional analysis methods for our complexity measures. So for instance, we checked for our synchrony coalition entropy measure, we looked whether there are kind of effects that one channel is kind of causing three other ones to be diverse in activity, and whether we would find any consistent effect there just locally and not globally. But we did not. Also, when we just restricted our measures to particular regions and looked at them amidst subjects, we still see everywhere kind of global trend that the complexity measures are higher for wake as opposed to unconscious. You know, there are occasional outliers, but we did not find anything consistently outlying. So there's no consistent local difference to the global effect. Now, what we actually were interested initially is whether it makes a difference if we take kind of multidimensional time series into account. That's why we came up with those measures, because it kind of tries to capture signal randomness of many channels at the same time, and not only one channel as many others did before. But it turned out that even if you look at only single channel randomness, or single channel complexity as measured by Lambda-Ziff compression, you get a very similar picture as opposed to the multi-channel thing. Now, this also works for other species. Yeah, for instance, for rats this year, you just measure the compressibility of single channels, and you see it's higher for waking as opposed to non-REM sleep. Yes, it's high for when the mouse is awake and when the mouse is in rapid eye movement phase, and it's low when it's a non-rapid eye movement phase. So it's kind of same as you found for humans. I mean, then the question is, of course, yeah, where does it stop? Does it kind of work for everybody? Yeah, does it work for macaque and elephants and whatnot, and even other species like octopus with very, very diverse and neural architecture? Or, you know, Tree of Life is a big place. So to what extent can we find a correlate, a neural correlate of conscious level that works for most species here? Another approach that we try to use to clarify a little bit what changes in neural dynamics when people fall into unconsciousness, when they're anesthetized or when they fall into dreamless sleep, is to look at models. There was a physical review paper recently showing some sort of percolation model of anesthesia. And what they do is you just feed some random time series at kind of an initial node, which is then projected to other nodes with a particular percolation probability of information transmission. And they show if you let kind of the information trickle through the system, percolate through it, a bit like liquid going through whatever, some material. That's where percolation theory comes from initially. Then if you measure the output signal, you find very, very similar changes in the power spectrum as you do for EEG when propofol is given. So that's one interesting model we'll look closer at soon, because it's very simple. You just have one parameter changing and you get the power changes that you see in EEG when propofol is given. Another model we're looking at is Stewart-Landau oscillators. So you just have a bunch of complex numbers which are oscillating, right? They're kind of circling around here, and with some natural frequency, and then they interact with all the other oscillators that sit somewhere else, given by some connectivity matrix. Yeah, it's here kind of whether they're connected or not, two oscillators. And you have some coupling strength. It's kind of the general form of the Kuromoto model, if you know that. And then you also get some time series that may look like real time series. And there was a paper out of people that claim that they have, with this model, reconstructed certain signal features that you also see for real EEG. So these people play with phase lag index, and they just show that the model network displays for certain signatures the same as the real EEG network. So those are just two examples of models that try to help us better to understand how anesthetics or other changes of conscious level affect neural dynamics, and to what extent our measures, or what our measures capture. So thank you very much for your attention. Please feel free to ask questions.
Questions?
So if you want a consciousness meter, what's the best of the bunch right now would be what?
The Casali-Massimini method, the zap and zip, how it's called. You give a magnetic perturbation, you look at the response signal, and you see how diverse the response signal is.
Okay, and so that's a bit unfortunate because I don't know how that all works. I was hoping you were going to say also W compression, which I do.
It has something to do with compression, yes, very much.
Well, let's just pretend that the LZ was the best, right?
Okay.
So we just pretend it was the best.
What is the level zip of the response to the stimulation?
Yeah. See here.
So the response matrix.
Okay.
You look how random is this binary matrix.
Sure. So if that was the best, I mean, what light would it shed on how the brain works or what's going on or anything?
Yeah, I mean, one big point that this shows is kind of long range connections in the brain break down when you lose consciousness, and you see this. I don't have a video of this, but you know, here you kind of see at least a little bit how here the green. You see my mouse there? Yeah, you do. The green star is where the brain was magnetically perturbed, and then the black is kind of the response activity of the brain. And then you see how this response signal travels around in the brain a bit. It goes to all corners and then comes back a little bit. And this is for the awake case. For the awake case, it goes kind of everywhere, and for the unconscious case, it just stays local and it's very quickly over. So and this shows you that these brain regions are not as responsive to transmit information to further brain regions when you are in the unconscious state as opposed to the awake state. That's, for instance, one lesson you could learn from that.
I mean, with the local zone thing, I mean, although it's a really clever algorithm, what's clever about it is not its kind of general strategy, which is just the standard thing of, you know, find them, repeating subsequences and introduce codes for them. And it's just what's clever about it is that it avoids the need to communicate the table.
Yeah.
So I guess if it was, you know, if LZ compression was a really good indicator of anything, then you'd have to sort of go back one step and say, well, what I'm really looking at is a detector for the intensity of repeating subsequences. Does that maybe that fits into what you just said about long range and short range effects? Maybe short range effects would show up more in short repeating sequences on the EEG or something.
It's of course always a bit hard to say. Depends a bit on your modality. Yeah? When you have EEG do you actually just at the surface you get a very superimposed signal of all the highly intricate activity which is going on below. So, 10 to the power of 11 neurons doing crazy things, and you're just on the surface and trying to see some very coarse superposition of all their activities. So such conclusions, you should always be careful, because it just depends on how close do you get to the activity. I mean, the depth electrode is a different story, because there you're very close in it, and you don't have that many artifacts and not that much superposition of activity. But still, I mean, as you saw, for instance, in sorry. Oh no, it's at the end. Sorry. Where they had these depth electrodes with little here. You have these unit activity, and there you can see actually how you get these time series from single spikes. And given maybe this activity here, you can. I mean, it depends always at what level you try to interpret what you're measuring.
Yeah, I think there's a key thing that there's quite a difference in how you interpret it, whether you're measuring the complexity of the response to the TMS versus just the spontaneous activity. Because when you're measuring the complexity of the response, then the complexity will depend on how far the stimulus is spread across the brain. So you really see complex stuff across the whole brain. You don't just want like some big black bit of your thing where like everything's just 0, 0, 0, 0, 0. Whereas for the spontaneous activity, it's you've got no threshold. Everything's just going to sometimes be defined as active and sometimes not active.
So why limpal zip? Why limpal zip? I mean, it seems like if you're looking for these long transients, isn't limpal zip that kind of overkill? Kind of just want some kind of bin distribution over time, the period of time, how far it's spread across the brain. Why limpal zip for the TMS stimulations? Basically, you say it's quite clear cut, right? It's just a local
area. It's measuring
stimulation.
two things simultaneously, so it's measuring how far it's spread. But if it was to just spread everywhere and then everything's just on, then that's no good. It's the fact that it spreads in a severe homogeneous way, so it will ignite one bit of the brain for a bit, then it goes off, then it reverberates around, comes back again, and so it's spread far and it's spread in an inhomogeneous way with complex activations.
So I guess the question is, do you see that it spreads far, but not in a complex way in the cases when consciousness is low?
When consciousness is low, you can ramp up the strength of the stimulation, and then it will spread far, but it will just flood the system, and everything will be on. There's no complex response.
I think Chris's question is there something about level ZIF complexity? Because if you look at details of the algorithm, is something we can learn from that? And if it's not something about level ZIF, then we can roll back to something more simple, right?
Well, that's right, because in fact, one of the cool things about level zip is it's kind of scale invariant in the sense that, it'll happily chase after, really, really long subsequences. It's not, whereas, a lot of other things, when you're calculating an entropy measure, you're nearly always bidding things up in a certain way, and then you kind of, you've guessed your scale in advance, whereas level zip, you don't have to do that. So I don't know whether that would be that might explain some of the difference. I don't know.
So I think, it is a nice thing that it is kind of invariant. It is invariant to how strong the stimulus is. Level zip is a powerful measure. I agree.
Have we got a question at the front, then the back, and then Manuel?
Not quite as technical. I was just wondering if there's been any studies into how meditation affects levels of consciousness.
Yes, there are studies. Christoph Koch, you can look up for that. So he found a few signatures that are there after in long-term meditators. For instance, power spectrum, you see that it changes, but not in terms of signal complexity. I don't think that anyone did any of those complexity measures. we tried to do it, but I just applied it once to 5-minute intervals, and I didn't see a difference. But that was probably not a very thorough study. But there are other signatures that you find very cleanly for meditative people. So Christoph Koch experimented with these Tibetan monks, and he found very clear power spectral changes.
Cheers.
Yeah, I was just wondering what your thoughts were about the relationship between complexity and consciousness, because it seems to me, I mean, do you think in the context of a brain it's always a good indication of consciousness? Because I mean, you could have a brain, I suppose, theoretically that was producing white noise, that wouldn't be progressive at all. It wouldn't be doing anything kind of intentional, goal directed, and so wouldn't.
Yeah, very good point. But for the brain, it has a certain architecture. These things look a certain way and they work a certain way. They're just not random number generators. So you can then rely on you can just use anatomical arguments and say, if we find such white noise-like activity in the brain, then this means that there's a lot of very complex internal activity going on. So, there's a reason to believe just by using anatomical arguments that given you measure high randomness, it does not really reflect the underlying complexity. It's just at the surface it looks random, but below there's a lot of very highly complex and complicated stuff going on, where this randomness is just the superficial proxy for it.
All right. Sorry, I wanted to follow on from that question about compressibility and randomness. So you're saying, in the brain there's a lot of structure and anatomy. The rest of it means that you see randomness, that it's likely to be complex information processing. But if you identify incompressibility with conscious level, you're left in the position where somebody who wants to increase their conscious level, a right thing to do would be to implant things in the brain that make it go random. That somehow doesn't seem right.
Well, I mean, so far we just claim it is a correlate of conscious level. We don't say it's equal.
Isn't there a causal in front of that correlate sometimes?
Say again?
Causal correlates?
Yeah, I mean, sure, Tononi and Koch, they go further, but we don't go there. We just say, here we have another correlate of conscious level, and there may be connections to certain theories, but we do not equate apparent randomness with conscious level.
But you kind of hinted at this before, because the complexity measures have a peak interim between completely integrated and completely segregated, right? Whereas your randomness measures just goes up.
Yes, that's true.
So basically, there is a story where the complexity measures is a little bit more sensitive to this interim period. You don't want complete randomness, so putting things in your brain and just do random noise would be low. Having a brain that does nothing at the low, and there's some kind of interim position. But what kind of Michael's found that even just these Lempel-Ziff things work really well, right?
Yeah.
Which is, I don't know, what do you feel about that?
I think, sure, there are these two terms of complexity. One is a dynamical systems word of it, that complexity is something in between complete order and complete randomness. So complexity measure should peak in the middle of the two and be low for perfect order and also low for complete randomness. Now, it could be that what we pick up with these measures is if you have a complexity measured, let's say it's a U-shaped curve, then we maybe just be on one side of this U-shaped curve with our linear randomness measures.
So how do you argue that then? So why are you on that side and not the other side?
Hard to say, I don't know.
Okay.
Yeah.
Well, I mean, another way of looking at it is, you actually need a complex algorithm or complex physical structure in order to generate random activity. I mean, like generating truly random numbers is very difficult to program, so that's always another way of...
I think you can just have a
Nice hot cup of tea.
yeah, like a hot cup of tea. Do you need any structure to cause randomness?
Sure.
Emotion would be good. A head full of gas.
Yeah.
But it doesn't have to be randomness that's actually driving the incompressibility. I mean, could it not just be that the brain's generating all the data so that
Yeah, definitely, yes. That's definitely an option, of course.
But then there's more going on in a random string, right? There's loads going on in a random string.
I think no, but I mean, you know, that's just what I tried to say earlier. You measure what you measure and what's actually going on underneath what you're measuring. It may not be the same thing.
So Michael, we've talked about this before, but so you've done this for pro-performance sleep, but of course ketamine induces unconsciousness in the opposite way to propofol in terms of its effects on brain activity.
Yeah.
So in that case, your complexity measures show low complexity, but
Would be very interesting to check. Yeah. Oh, they don't have it. Sorry, I just have xenon and propofol. Okay. Would be very interesting to check different substances. Indeed, I mean, what we we also looked at LSD and seeing if the psychedelic state may even display a more random. Do they have this ketamine? No, just downers, no uppers. So of course, yeah, of course.
so on the other side, of course, on the other side of your so with regard to your comment about putting random generators in the brain, that's what ketamine does. So
Cheers. Yeah, I should check whether there is.
So no one knows what level Zipf does with ketamine, is that right?
That's a good question. I have to Google it.
I was just going to make one comment about about randomness, which is that high levels of randomness in the communications channel indicate that the channel is being used efficiently. Low levels of randomness in the communication channel indicate that it's being used inefficiently. So, but it doesn't follow.
So is that really?
Yeah,
so,
yeah. So the number of bits that are being transferred.
Yeah. If you're assuming that there is a receiver and a sender, right?
Yes.
Yeah.
Uh,
So we're gonna. Oh, it's gonna be very quick.
It is a really quick one. I was just wondering when you were doing the mouse brains of how you determine what voltage threshold to use, and if you think you lost any data by having it high.
So we didn't do any mouse studies.
Oh, no, sorry. Do you know how they did?
So here or
Yeah, both of those sort of the. So you said they fired, or they were signaling when there was they passed a certain threshold for the voltage.
yes, this study here.
Yeah.
Okay, yeah.
I was wondering if you knew how they determined.
I mean, there's a lot of bioengineering going in there. So those are the people. I would have to look it up, the details. But you have to smartly genetically modify the neurons of the mouse such that you genetically modify the neurons of the mouse, and then you shine light on them, and they only shine the light back if the voltage is high enough. So that's actually how this works. But you know where the thresholds are and so on, I don't know. Okay.
Cool. All right. So we're going to continue in IBS for a 5.